our last speaker from ETH Zürich, Kladeftira. She will present a project called the Digital Bamboo Pavillon, where she combined with her team a natural material, bamboo, and the printed connectors to a new kind of construction system. And when you see it, it's unbelievable, great work they did in Zurich. So welcome, Marirena.
Thank you very much for the invitation and for giving me the opportunity to speak. I will try to share my screen. Okay. So again, thank you very much. My name is Marirena Kladeftira. I'm a doctoral researcher at ETH Zurich, as you mentioned, and my research focuses on 3D printed connections for non-standard space frames, and today I will present without the digital bamboo. So I want to start with some key points that are kind of also driving force for the work that I do. So by 2050, 3 billion people will actually need access to housing and infrastructure. And this will be, of course, evident in the built environment. And since little has changed in the pipelines of construction since more than 50 years now, the AC sector is currently the least efficient compared to all others in the economy. And apart from inefficient, we also know that it is a massive contributor to climate change, but this is only the first wave of our problems. There has been an increasing shortage of resources, so materials that we primarily build with, and it is my opinion that this will be one of the biggest challenges that we have in the coming years. And in parallel to material shortage, we also face shortage of skilled laborers and fatal accidents on sites. And at the same time, all of this is happening in a world of digital trends where technology is not only a necessity, but also a lifestyle. And so, how can this technology provide solutions for the problems that our industry is currently facing? And I always refer to this architecture of systems because I believe that we need to rethink entirely our building systems and process chains. So most of the future construction will actually be in the global south. So instead of transferring models of central and northern architecture, I'm also interested in identifying ways in which technology can enable us to entirely reinvent the way we will construct in local economies. So bamboo grows natively in the global south, and in recent years we have seen a worldwide interest in bamboo with new farms in Europe, like the one you see here, or in North America. And the interest is well founded, of course. Bamboo is a scalable material for construction. It has a great strength to weight ratio, while its growing and harvesting cycle is very short compared to other biomaterials like timber, for example. And we can harvest fully grown poles as early as 5 years. But we often associate these biomaterials with vernacular design and bamboo specifically also with this ad hoc temporary construction in Asia mainly. And structures typically made from bamboo are rectangular frames or grid cells because of their bending capacity. And these forms continue a long tradition of low-tech joining methods. But thanks to its natural form, bamboo is also an excellent candidate for replacing energy-intensive materials like steel or aluminum in space frame structures. And space frames are notably very efficient structural systems that use materials optimally, resulting in lightweight construction. And if we can do more with less, resources are adequate to take care of everyone. So the problem of utilizing bamboo in space frames results exactly from its natural shape, so deviations in diameter and orientation of its fibers. So how can technology help here? I'm discussing in my thesis a new construction chain that is based on decentralized prefabrication. So digital design allows the design planning and control of all the phases down to the production data. So we no longer need to produce drawings from manufacturers and contractors, but our design data can be directly translated to 3D printed building elements in a facility close to the construction site, And then in combination with local materials that are non-standard, very often we can build larger and performative structures. But to this day, bamboo trusses are realized by retrofitting standardized systems. And what we proposed instead is to use this new powder bed method called multi-jet fusion for architecture to create light nylon parts that can mitigate exactly these inconsistencies in bamboo poles. And we started to envision different connection systems for bamboo. And some are based on typical mechanical connections with pin or screw fasteners, while others explore snap fit mechanisms. And we tested different connection systems and typologies of structures. And all these tests were instrumental to identify the best connection system for bamboo. And here you see the failure intention of a pin connection on the right side and the failure of our developed system on the left side, the knots. And what we did with this knot is to basically distribute the stress over a larger area in contrast to the pin that concentrates the stresses in one point and also allow for a higher tolerance in the connection. And of course, this was also followed by more testing to improve the geometric system. And this evolution of the joints was very important so that the connection does not represent the weakest point in the structure. At the end, we had this rotational modular dry connection that we can just click together like Lego pieces and fasten with zip ties. So it is a fairly complex object that comprises different parts. The core, the limbs, the integrated add-on features like the connection to the shading panels and post-tensioning cables, the assembly information, and those caps. And those can be mass produced to reduce time and cost, for example. So all of this was made possible through a computational design pipeline that was developed. And in parallel to that, we were also investigating what kind of architecture one can build with this system. So we wanted to demonstrate the opportunities of 3D printing and the new architectural vocabularies that it allows for. So we designed a bespoke space frame with 2 axes of symmetry in order to also reduce the logistics. And with the help of my colleagues at the Chair of Structural Design at ETH, we used graphic statics to determine the topology and hierarchy of the structure, which was post-tensioned to limit the tensile forces in the connections. And we also performed structural analysis, and we could identify the elements that needed reinforcing, and those were replaced by a triplet of bamboo poles, thanks to the flexibility of the connection system. So again, all of those details could be seamlessly embedded into the 3D printed connections. At the center of the structure, as you may have seen the picture, we have a keystone connection where 18 bamboos and 6 post-tension cables meet. And the nylon here was not sufficient to take all the forces needed. And this is why we designed a new connection that was fabricated with direct metal laser sintering. And although the cost here is higher for 3D printing metal, what we achieve is to maximize by 300% basically the members that are connected. But also we can see how a hybrid scheme of utilizing many different AM technologies can benefit the design, but also mitigate the costs that are associated with advanced technologies. The structure was covered with a lightweight textile panel in a process that we call add-on 3D printing, and it basically combines a mesh textile in kind of a sandwich layer of extruded UV-resistant thermoplastic that is just enough to stiffen and form the panels. And those are also again directly connected to the printed joints and mounted with dry connections. So this process allows the production of ultralight panels, and the 3D printed plastic is applied only for forming and stiffening. And here you can see an overview of all the processes. So all the digital frameworks that we develop allow this planning and fabrication of these non-standard structures. So we had more than 380 joints that were printed, but aside from all these different 3D printing technologies that we use to enable the structure, We also used things like robotic arms to basically efficiently mark all the lengths for the bamboo poles and cut them and so on. So the entire structure is basically entirely fabricated with digital methods. So we had more than 2,000 elements in total that we could fabricate within only 1 month. And we formed this kit of parts that we shipped in these 4 boxes to Venice, where the exhibition of the digital bamboo took place. And there in Venice, we could pre-assemble parts of the structure near the construction site in only 5 days, with the help of untrained staff that had never experienced this building system before. So we could mount the whole structure that weighs only 200 kilos in just 1 day with only 3 people on site. And this pavilion covers an area of 40 square meters and only with 5 kilos per square meter. So you can imagine that this is a super light system. And just to give a point of reference, because I'm talking about lightweight architecture, what you see in the green bag on the bottom is the same weight of the whole structure measured in construction waste. So maybe to conclude, what does it mean to build sustainably, and what did we manage to achieve with this research? We used monomaterial elements to avoid layering and composites, and this ensures basically that there's no cross-contamination between the different materials during disassembly, and that materials can be then recycled or reused. And we used a local biomaterial from a Swiss provider instead of carbon-intensive steel or aluminum. And we developed a modular structure that can be assembled on-site from components that are manufactured off-site, thus supporting safe and rapid deconstruction and material reused. And we sheltered the space with minimal volume, weight, resources, and we made it happen with a low-cost, high-tech system with a small carbon footprint, basically. So thank you very much. I will stop here. I'm happy to take questions.
Yeah, thank you for this great presentation.